So how do you know what's different, right? You're looking at 50,000 things. You know, say you've got two conditions. How do you know what's truly different, that truly impacts your system, right? And what we find is that most genes are pretty much, if you're looking at the same tissue type and maybe one has a disease and the other one doesn't, it's not, you don't necessarily get a lot of genes that are changing. How do you find the select few that are actually impacting your system? And for this class, use statistics, right? So you guys have gone over t-tests, I'm sure, right? Yes. Did your teacher tell you the story about the t-test? Anybody familiar with this story? It actually developed through Guinness Beer, the brewery. So this is the early 1900s. There was a guy pictured right here. His name was William Gossett. He was kind of slumming. He was working for the Guinness Brewery. And you're going to hear there's lots of different versions of this story. This is the one I've heard, and this is the one I pretty much believe. But, so he was actually a student of Carl Pearson. Does everybody know who Carl Pearson is? What's that? Pearson correlation, right? Yes. So he was one of his students. And, you know, the university was very, this is back in England, so very highfalutin. He wanted to make some more money, so he actually did a sabbatical at Guinness Brewery. And Guinness had this thing where, they wouldn't ship their beer farther than 60 miles from Dublin because they thought it would affect their beer, and then word would get out that their beer wasn't very good. And there was this huge outcry, as you can imagine. This is the Irish here. I'm part Irish, so I can make fun of them. They're like, give us beer, we don't care. Even if it tastes a little, not as good as in Dublin, we don't care. Just send us the beer. So Guinness wanted to make sure that, there was no difference, that if they shipped it farther, that the difference would be negligible. So they basically got him to come up with a test to determine whether there was any difference. And so, as you can imagine with beer, there's lots of things you can measure, right? Carbonation, you can measure, the the index, the reflective index, or I can't remember what it's called. But there's a lot of things you can measure. So what he did is he actually measured them in Dublin and after they've been transported and see if there was any difference. But this was his big breakthrough. By the way, he found no difference, and they were able to ship the beer, and England or Ireland rejoiced for the next 125 years. But that was his big breakthrough, right? Is that nothing you measure, that every time you measure something, you're not going to get the same answer. And they've kind of saw this with populations, that anything you measure will have a distribution. And statistics up until that point was all about these huge populations. But what he said was, well, we can measure a subset of that and basically kind of estimate that distribution of the entire population. And if we can do that, then we can determine what's different or not. Human height's a really good example here. Does anybody know, so these are all ladies arranged from shortest to tallest. And you can see this nice bell curve here, right? What do you think anybody guess what the average height of females is? 5'4", 5'5". Probably around here it's probably 5'5", because, we get all kinds of growth factors in our foods, so it's about 5'5". When I say that, though, so does that mean most women are 5'5"? Did somebody give an answer? Are most women 5'5"? No. Are the majority of women 5'5"? No, they aren't, right? It's a small select, but that is the average. And that's what we kind of look with biology stuff, is that if I measure a gene, I don't expect every time I measure it to be the same, and that when I measure it, I can kind of figure out this distribution, okay? And now that we have a distribution, we can do all kinds of things with it. We can find that central point, the mean. We can do standard deviations, which will give you the spread of the data. We can go 2 standard deviations out and get the 95% confidence interval. Also, And you've heard of tails in statistics, right? This is kind of where it comes from. What are the odds that I get something out of the 95%? That if I'm comparing two hills, I would hope, and that's what statistics does, is hope that it crosses no farther than this point here. And let me show you a graph to kind of demonstrate that. Oh, also you have other types of distribution. So I will say, from my standpoint in gene expression, I see pretty much normal distribution for most genes, but there are other types, and we can run tests to determine that. So here is again, this is, I was talking about human height. I think it's a really good example because it's, people get that. Especially, I teach this to high school kids, and they're like, oh yeah, we understand that. So if we have, so this is human height, this is a distribution for females and males. At what height, so if I'm calling somebody on the phone and he says, hey, I'm with somebody who's blank tall, what would be that height where it would be an equal chance at being a male or female? What do you think? Can you guys see that up there? 5'7"? Wait a minute. Wait a minute. 5'6", 5'7"? Yeah, 5'7". Yes, you're correct. Yeah. Now that we have distributions, we can ask other questions, right? Say, I'm talking to the same person. He goes, hey, I'm talking to somebody who's 5'9", right? What would be the odds that they're talking to, say, a female? And you can just estimate. What do you think?
10%.
I love this. You guys get that. Like, the high school kids never even get close. Yeah, right? If he says I'm talking with somebody who's 5'9", that's only two inches taller than the point where it's an equal percentage. Now we've changed dramatically. Now it's a 90% chance that he's talking to a male and female, and 10% chance he's with a female. And again, this p-value is critical, and especially in biology. So based on this example, do you think human height is a good way to determine who's male and female? No, right? And that's what we look for is, when I want to use a gene to determine what's going on in a disease, I want this p-value or this overlap to be as small as possible. Okay? So you can see how this works, right? That this, if I can measure all the genes in a person, and I've got a bunch of people with a certain disease and some people that are normal, we can basically look at the gene expression, do our statistical tests, and then we can get a list of genes that are different, right? But this doesn't say everything. This is just the start of our journey, really, right? Getting this list is easy. How does it actually impact what we're actually looking at?